The topic for today is capacitance. A capacitor is a device that stores electric charge. They're very useful and have a lot of great applications. They're used to tune frequencies in radio receivers. They're used in intermittent windshield wipers, filters and power supplies. They can eliminate sparking in automobile ignition systems. And they can be energy storing devices in flash units. So they have a lot of different uses in technology. Basically, we've talked about capacitors a little bit before. I'll show you the simplest configuration. It's a device that stores charge and is one where we have essentially one plate that is positively charged and one plate that's negatively charged. We define capacitance, the physical quantity, as charge divided by potential difference, or voltage. The units of capacitance, so it's a coulomb per volt, and we use the unit of farad for capacitance. 1 farad is a very, very, very large capacitance. In fact, you're more likely to see capacitances on the order of microfarads, 10 to the minus 6 farads, or even picofarads, 10 to the minus 12 farads. So if you see a 1 farad capacitor, that is an enormous capacitor. In calculations, as long as we can determine a potential difference with some of the techniques that we used in the previous class, given a finite amount of charge, we can calculate the capacitance of a certain configuration or device. So as you see, we have this nice parallel plate capacitor. As you might recall, the electric field between the plates of such a capacitor, especially if it's a very long capacitor, long in length, is directed from the positive plate to the negative plate. We know that these are conducting plates, therefore the electric field, as we talked about last time for a conductor, is equal to the surface charge density divided by the constant epsilon naught. So that's the electric field between the plates of the capacitor. We also know that the potential difference between the plates can be written as the electric field times the distance between the plates. Let's call that some distance d. So given a capacitor, a parallel plate capacitor with a distance between the plates of d, where the plates have an area A, we can get an expression for capacitance. If it has some amount of charge, I can write it in this way. I can write my electric field as sigma divided by epsilon naught, which by Gauss's law I can write as Q over A epsilon naught. Voltage, as we said, is electric field times the distance between the plates. Therefore, I can write the voltage as QD over epsilon naught times the area of the plates. And then finally, I can write my capacitance as just Q divided by this factor, or C is equal to epsilon naught times A over D. So this is a nice working expression for capacitance. As you can see, you can increase the capacitance of a capacitor if you can increase the area of the plates, or if you can decrease to some limit the distance between the plates. So we can do some nice simple examples of calculating capacitors for different geometries. For example, suppose I have a cylindrical capacitor. So now what I've done is I've taken my parallel plates and turned them into a cylinder. I've rolled the plate into a cylinder. And let's say I have the outer plate has a minus Q and the inner plate has a plus Q on it. And let's say that the inner plate has a radius A and the outer plate has a radius B. So what we can do is to calculate the capacitance, what I would do is use Gauss's law. I can draw a Gaussian cylinder in between the two plates so that I'm enclosing the plus Q from that plate. Now all I have to do to get the capacitance is, of course, find the electric potential of this cylindrical capacitance. So once I do that, I will be able to calculate the capacitance. I'm going to set it up so that VB minus VA is equal to minus the integral of E dot ds, where ds is the distance between the plates. The electric field for a cylinder, you remember from Gauss's law, I draw a Gaussian cylinder in between the two cylinders. And I know that, let's assume that we have a constant charge per unit length of lambda. So by Gauss's law, remember E dot dA is Q enclosed over epsilon naught. In the case of the cylinder, the field is going to be a constant everywhere around that, along that Gaussian surface. Remember, the field is going to be pointing outward from the Gaussian cylinder in all directions. So I can write E times the area is equal to the charge enclosed, which is plus Q divided by epsilon naught. I can then say the electric field is just going to be, I can write this as lambda over 2 pi r epsilon naught for my electric field. Write that out specifically. E times the area, which is 2 pi RL of the cylinder, is equal to lambda times L, charge per length, divided by epsilon naught. As you see, the L's cancel as they must, and we get a nice expression for the electric field. I can put that expression in my electric potential expression, so that's going to give me the integral from lambda over 2 pi epsilon naught integral dr over r from A to B. Will give me a minus. And so when I do the integral, of course, I'm going to get the log of r. When I put my limits in, I'm going to get lambda over 2 pi epsilon naught log of B over A. I'm going to take the positive, I'm going to take the magnitude of this potential. Capacitance can never be a negative quantity. In fact, as you'll see, capacitance is actually a geometrical quantity. Well, you can see that by the equation. Look, we have a constant times an area over a distance. There are no electric quantities in there, such as charge or voltage or any of the like. So this is just a geometrical expression. Therefore, capacitance can never be negative, so I'm always going to take the positive value for the potential, and I can say then that I can write the capacitance as lambda times L divided by lambda over 2 pi epsilon naught times the log of B over A. And so that will give me the capacitance for a cylindrical capacitor. Oftentimes when you use capacitors, you don't use parallel plate capacitors like the first example that we do. They're oftentimes going to be wrapped in a cylinder. Another interesting geometry is the spherical capacitor. So suppose I have a sphere, two spheres that is, inner sphere radius A, outer sphere radius B, plus Q on the inner sphere, minus Q on the outer sphere. Suppose I want to calculate the capacitance for that sphere. Once again, I'm going to use the flow chart. C is equal to Q over potential. Potential is equal to minus the integral of E dot ds from A to B. And then, of course, the electric field for a sphere, we can do that immediately, don't even have to use Gauss's law. It's just going to be Q over 4 pi epsilon naught times r squared, where r lies between A and B. And so if I insert this into my electric potential equation, I'm going to get that V, B minus VA, is equal to Q over 4 pi epsilon naught times the integral of dr over r squared from A to B. There'll be a negative in there, even though we're going to get rid of the negative sign ultimately. So that the voltage then is equal to 1 over 4 pi epsilon naught. That would be Q over R. So my capacitance would just be equal to 4 pi, oh, and I must put in my limits. Let's not get ahead of ourselves. V is equal to 1 over 4 pi epsilon naught, and that's going to be 1 over B minus 1 over A times Q. And I can write this then, C is equal to Q over V. I can get a common denominator. And notice the Q's cancel, and I end up with 4 pi epsilon naught A times B over A minus B. So first, this would be the capacitance for a spherical capacitor. By the way, if we wanted to look at just the capacitance for a sphere where the outer sphere was extended to infinity, we could do that. All we would do is remove the B from the denominator, and then we could just cancel the A's. That would be 4 pi epsilon naught times B. Sorry, we would eliminate the A from the denominator. I'm sorry. Cancel the B's. That would be 4 pi epsilon naught times A. So that would be the capacitance for a spherical capacitor. Oftentimes, what we like to do with capacitors is take combinations of them. So I'm going to show you two ways that we can combine capacitors. This is going to be something that we'll use not only here, but in the next unit when we talk about resistors. We'll talk about combinations of resistors in almost the same way. But for now, let's talk about combinations of capacitors. So let's consider the following situation. Suppose I have this configuration. I have two parallel plate capacitors, and they're connected to a battery. Now, when I engage the battery, notice what's going to happen. If they're connected in this way, we call this a parallel combination of capacitors. When they're connected this way, if I engage the battery, the left plates will all become positive, the right plates will all become negative, until which time as the voltage between the plates is exactly what's coming out of the battery. So in a parallel situation, let's call this capacitor C1 and C2, the voltage across C1 would be equal to the voltage across capacitor 2, and it would just be equal to the voltage coming out of the battery. That being the case, the charges, though, would be the same everywhere. When I have electrostatic equilibrium, the charges are going to be the same on each capacitor. So in this case, Q1 is equal to Q2 is equal to the charge that comes from the battery. When we have electrostatic equilibrium, there'll be no flow of charges, and we'll have these conditions applying. I should say, that is, let me fix that a little bit. The sum of the charges coming out of each capacitor will be the charge that the battery holds. So in that case, capacitance being equal to Q over V, that's going to be equal to Q1 over V plus Q2 over V. So my equivalent capacitance, that is to say if I were to draw a circuit that had just one capacitor and one battery in it, so here's the circuit symbol for capacitor, two parallel lines, circuit symbol for a battery, the capacitance would just be equal to the sum of the capacitors. So C1 plus C2 would be equal to the equivalent capacitance. So if I take these two capacitors, that would be the equivalence of having one battery and one capacitor that had an equivalent capacitance, Ceq of C1 plus C2. That's what we have for capacitors in parallel. In the case of series capacitors, that's a different story. Suppose I have the following situation. Suppose I have my capacitors lined up like so. Here's one capacitor connected directly to another capacitor, and then to a battery, like so. When I engage the battery, at this point, the electrons from the battery are all going to pile up on the right-hand plates of the capacitor, making the left-hand plate positive, the right-hand plate negative, and the same for this plate as well. And it will be such that we'll have electrostatic equilibrium when the charge on each capacitor, so this is C1, this is C2, the charge on each capacitor will be the same as and also equal to what comes from the battery. The battery voltage then will be equal to the sum of V1 plus V2. That being the case, if I put this all together, it turns out then that if I want to calculate the equivalent capacitance for a series circuit, this equivalent capacitance can be written as 1 over C equivalent is equal to 1 over C1 plus 1 over C2. And for however many capacitors you have in series, it will be 1 over plus 1 over plus 1 over. So you notice that the equivalent capacitance in a series circuit will be less than the value of any one capacitor in the circuit. So of course, these are two ways that we can configure circuits of capacitors. And of course, the third way is to do a combination of series and parallel capacitors. We can do an example of one of those right now. Suppose I have the following circuit, and I'm going to do a circuit diagram instead of the cartoons of capacitors and so on. I have 3 capacitors in a circuit with a battery. I have a 12-volt battery. I have a 4 microfarad capacitor here. And I have a 5 microfarad capacitor here, 5 microfarad capacitor here, and I have a 7 microfarad capacitor here. And the question is going to be, first, find the equivalent capacitance of that circuit. Secondly, find the voltage across each capacitor and the charge on each capacitor. So there's a fairly simple algorithm to making those calculations. And the first thing you want to do, always go to the farthest point from the battery. When I do that, I go as far away from the battery as I can. I look at these two capacitors as being parallel to one another. And so I can write the sum of that as, so I have a 12-volt battery. I still have my 4 microfarad capacitor up here, but I have 2 capacitors in parallel, so they add. So that's like having a 3rd capacitor here with a value of 12 microfarads. So now I have 2 capacitors in series. So the next step is to say, well, for 2 capacitors in series, I know that the equivalent capacitance, 1 over the equivalent capacitance, is equal to 1 over 4 microfarads plus 1 over 12 microfarads. So that's going to be 3 over 12, and 1 over 12 is 4 over 12. And therefore, C equivalent is going, I got to remember to flip them, C equivalent is going to be equal to 3 microfarads. So I have an equivalent circuit that has a battery with 12 volts and a capacitor with 3 microfarads. This is my equivalent capacitance, 3 microfarads. When I want to find all of the charge and voltages, I have to work backwards. So what I do at this point is I say, I've got a 12-volt battery, a 3 microfarad equivalent capacitance. That will give me 36 microcoulombs would be the equivalent charge that I have, or total charge, I guess I should call it, on that capacitor. I've got all the information I can get from that circuit. Let me go back one circuit, and this equivalent capacitance is a combination of these two series capacitors. That means each, because they're in series, the charge is the same, so each of them has a charge of 36 microcoulombs. And the voltage across this one would be Q over C, so this would have an equivalent voltage. This would be 3 volts. This would be 36 over 4, or 9 volts, and of course that's good. It adds up to the voltage in the battery, coming out of the battery. I'll go back one more step. I notice that my 4 is fine. I'll leave it alone, so this is 36 microcoulombs. This is 9 volts. This equivalent capacitance here, this 12 microfarad capacitor, is actually a parallel combination of the 5 and the 7. Both, since the capacitors are in parallel, both of them have the same voltage across them, so each of them has 3 volts. And by the equation for capacitance and charge, if I multiply the capacitance by the voltage, I'll get the charge. So this would be 15 microcoulombs, and this would be 21 microcoulombs. As it must be, the two of them should add to 36, which they do. So that's a nice example of using capacitors in series and parallel. I'm going to set one more example up in the short time that we have. Suppose I have the following situation. Suppose I have capacitors configured in this way, and I have a 6 microfarad, a 3 microfarad, 12-volt battery, 8 microfarad, and a 24 microfarad capacitor. I want to do the same thing. I want to find the equivalent capacitance, find all the charges, and all of the voltages. So to do that, I'm going to deal with these two guys in series first, these two guys in series next. That will give me an equivalent circuit that looks like this. 1 over 6 and 1 over 3 will give me a combination of 2 microfarads. And the 1 over 8 plus 1 over 24 will give me a combination of 6 microfarads. I now have a parallel combination, so I've got 12 volts, and I just add the capacitors in parallel, so my equivalent circuit is now a 12-volt battery with an 8 microfarad capacitor, because 2 and 6 is equal to 8 capacitors in parallel. The total voltage would be then charge would be 96 microcoulombs. The voltage would be the same, would be 12 volts here and here, because these guys are in parallel, so I have 12 volts and 12 volts. This will give me 72 microcoulombs. This will give me 24 microcoulombs to add up to 96 microcoulombs. If I go back to my original circuit, these two guys are in series, so the charge on each will be 72 microcoulombs for this guy and for this guy, because it's a series circuit. On this guy, it will be 24 microcoulombs and 24 microcoulombs. The voltages would be 4 volts for this capacitor, would be 8 volts for this capacitor, adding to 12. This would be 9 volts for this capacitor, and then 3 volts, again adding to 12. So you can see how this works very nicely for capacitors in series parallel configurations. You'll see more of this when we do circuits of resistors. Let's stop with this here. Next time I'd like to talk a little bit about energy in capacitors, and then we'll talk about dielectric.